Hey everyone, this is Dr. Walker. In a previous video, we just talked about the concept behind electric potential energy. So in this video 518, we want to go ahead and derive an equation for it. The first thing that is important to do is just to really link the concept of electric potential energy to that of gravitational potential energy. So remember that if you have a mass, m, then it has gravitational potential energy mgy, but it's always relative to some kind of reference point. We usually take the ground to be y equals 0, and so then it has a certain position relative to that ground. One way that we can figure out how the potential energy of this mass changes is by looking at the work done by gravity. And since gravitational force is a conservative force, which means that the work done by the force does not depend on the path. When that happens, we know that the work done by that force is equal to the negative change in potential energy. So we can do the same exact thing when we're looking at the charge. I have a note here that the electric force is also a conservative force. So let's look at the work done by the field as a charge moves within that field, and then we can figure out the potential energy from there. In this case, we're looking at a charge moving in a field here produced by two oppositely charged plates, but we can derive a general expression. The work done by the electric field is the integral of f dot ds, where we're talking about the electric force, and we can plug in the definition of the electric force, which is Q times E. And so we have the work is QE dot ds. We know that we can take the charge out of the integral, and so we have Q times the integral of E dot ds. What is important with dot products, what's important to remember is that it's the component of the motion that is in the same direction as the field that matters, right? Because that's what the dot product does. It takes that parallel component. So this is the general expression for the work done by the electric field as a charge moves in an electric field. Now what we can do is we can look at a special case here. And a special case is what goes along with this picture, is when the field is uniform. So the field between two parallel plates is uniform. So the work done by the field in this case is going to be Q, and then the dot product of E dot S, we can take it out of the integral, and in this case the charge is moving along the field, so we just get E d, where d is the distance moved by the charge. So this is a special case. Now that we have the work done by the electric field, we can find the change in potential energy of that charge as it's moving from one point to another within that field. So the change in potential energy of the charge is going to be the negative of the work done by the electric field. Once again, this is because the electric force is a conservative force. So we get negative Q, just the negative of what we got in the previous slide. The negative Q times the integral of E dot ds. And I have a special case once again. If we do have a uniform field, then the change in potential energy of the charge is going to be negative QED. I do have a special note here that a charge naturally goes in a direction such that it decreases its potential energy. This is very much like the mass again. If we consider our mass, if we place it in this gravitational field where it has that gravitational potential over here, what does it want to do? It wants to fall down, and lose all of that potential energy. It wants to decrease that potential energy. The charge wants to do the same thing. When it moves, here in this case it's a positive charge, when it moves to the right along the field, it will decrease its potential energy. We can look at the equation to check this here by just plugging in pluses and minuses. The change in potential energy, we have a positive charge here, so put a plus for the Q, and then the E is going to the right, since it always goes from positive to negative charges. So we have a positive for the field, and then the distance, well, we move to the right as well. Since we moved along the field, we know that a positive charge always experiences a force in the same direction as the field. So when we multiply a negative number by a positive and a positive and a positive, we do get a negative number for the change in potential energy, telling us that it does decrease. Let's look at a question. A positive test charge in electric field pointing downward will move from A to B, and what's going to happen to its electric potential energy? So pause the video, and hopefully this was just a refresher of what we just talked about. We know that it's going to want to lose potential energy. We just showed that. And we know that it's moving from A to B because a positive charge always experiences a force in the same direction as the electric field. To summarize, let's look at charges moving in an electric field and see what happens to their potential energy. When we have two parallel plates, we know that the electric field always goes from the positive plate to the negative plate. So in both cases here, the electric field is pointing to the right. Let's look at the case on the right first. We're going to have a loss in electric potential energy when a positive charge moves the way that it naturally wants to go, which is along the field, to the right. And a negative charge experiences a force opposite the electric field. So a negative charge naturally wants to go to the left, towards that positive charge. So in both cases, when the charges go the way they naturally want to go, they will lose potential energy. Now, if it happens that something is forcing the charges to go the opposite direction, then they're going to gain potential energy. So if a charge goes against the electric field, positive charge, which is also towards a positive, or if a negative charge goes with the field or towards negative charges, then it will gain potential energy. Once again, if you compare it to the mass wants to fall down, but if there's an external force that is pushing it up, that's going to cause that mass to gain potential energy. So that was it for this video. Hopefully you have a better understanding of electric potential energy.